Beth.
And I'm Beth.
Welcome to Physics with Beth and Beth.
Hello everyone, and welcome back to Physics with Beth and Beth. I'm Beth, and today we are continuing our exploration of AP Physics 1 Unit 8, which is on fluids, and we're going to be expanding on our discussion of fluid statics by talking about a new concept, pressure. Something that some of you might be feeling like you're under a lot of as we've been going throughout this physics unit, but hopefully we can relieve some of that pressure today by explaining a few things here. So pressure really isn't that bad, I promise. Pressure, we like to denote with just a capital letter P. Thankfully, we have enough letters in the English alphabet to talk about this one. And what pressure is simply a force that is spread out over an area. So we have a force, we're pushing on something, and that push is spread out over an area. You often hear people talking about things like air pressure. That's the force of the air pushing down on, for example, the area, your surface area, or the force of the air pushing down on any surface. So pressure is a force divided by an area. The units that we use for that are just the units of force divided by the units of area. So our units of force are, of course, our good old friends, the Newton. And units of area would be something like meters squared. So the standard international unit for pressure is newtons per square meter. However, we rename this and give it an honorary name. We often just call a newton per square meter 1 Pascal. So Pascal was a science man who did a bunch of cool science back in the day, so we named a unit after him, and that's 1 Newton per square meter. Now, if you think about it though, that's not a lot of pressure at all, because a newton isn't really all that much force, and a square meter is pretty big. Like this whiteboard is maybe a meter wide, maybe. So if we did like a square of this, so 1 Pascal is 1 Newton spread across all of that area. So that's not a lot of pressure. So a lot of the time you'll see things written out as like 1 kPa or kilopascal, which is just 1,000 newtons per square meter or 1,000 pascals. So nothing too bad there. If any of you guys have experience in chemistry, you might have been using a lot of different units for pressure. We like to change it up based on what units are convenient for the context that we're working in. So sometimes in chemistry, you're working with things that are really, really small or with things that are really, really big. So we switch up our units there. A unit that you might see a lot in your day-to-day, especially in the States here, are the units of PSI, which stands for pounds per square inch. So if you're driving your car and you're checking your tire pressure, that's the pressure, the force of the air inside your tire that it's exerting over the surface area of your tire wall. So pounds, how much force per square inch over that much area. In meteorology, when you're talking about things like air pressure, which is a lot of pressure, we often use units of bars or millibars, which will often be denoted like that, or even just units of atmospheres, which is denoted ATM. But if you're ever given things in these units, you'll also be given the conversion factors. So as long as you know that these are different ways of measuring pressure, and you can convert that to pascals, which is newtons per square meter, you'll be A-okay on the AP exam. Okay, so let's see. Pressure is a force over an area. So let's talk about how pressure can change in different situations. Well, first of all, we can make pressure get higher by increasing the amount of force. That makes sense, right? If I have a fluid like water or air pushing against a surface, if I say it's pushing harder or there's more of it that's pushing and I increase this force, then I'm going to have more pressure. That makes sense. We can also increase pressure by decreasing the area that a force is spread across. Because if I have something big divided by something small, then I get something bigger, right? Conversely, if I want to make my pressure decrease, I can do that 2 ways. I can either make my force smaller, or I can make my area bigger. Now, when I was in college, I was part of this little club called the Society of Physics Students. They do a lot of cool stuff. I would really recommend checking them out when you go to university. But one of the things that I did in this club was a lot of demonstrations on like science demonstrations for kids in elementary and middle schools. And one of our favorite demonstrations that we always did was called Bed of Nails. And so we would drag up one of my classmates in front of this audience of elementary school kids, and we would very theatrically say that, oh, poor Nate here hasn't been doing his homework, and so we really need to teach him a lesson. So we would lay Nate down, and we would get out this very spooky looking board that had dozens and dozens and dozens of nails pounded into it, and we would put that on Nate's chest, which we would then follow up by a cinder block or two, sometimes even a small child. And we would lay all of this out on Nate's chest, and then we would take a sledgehammer, once the children were safely removed, and break the cinder blocks on top of the board on top of Nate, or whichever one of my classmates was the unfortunate demonstration for the day. And at the end of it, we would theatrically remove the cinder blocks, and much to the surprise and dismay oftentimes of the students, because elementary school children are surprisingly bloodthirsty at times, Nate was perfectly fine at the end of every one of these demonstrations. And the reason for that was, yes, we were applying a lot of force over the surface of that bed of nails, but even though it looked scarier because there were dozens and dozens and dozens of nails pounded through that board, it was that exact thing that made it safe, because our force was being spread out across such a large area, not being spread out over just one nail head, but dozens and dozens and dozens of them. So because we had a large force divided by a very large area, the pressure wasn't all that much, and my classmate would never even get bruised. So that's one way that we can decrease pressure. So let's go through a quick little practice problem solving for pressure. Let's calculate the pressure that a 65 kilogram student sitting on a 5 kilogram chair exerts on the ground. And for the sake of this problem, we're going to be assuming that each chair leg has an area of 2.5 times 10 to the negative 4th meters squared. And we're also going to assume that the student is actually sitting with all 4 chair legs on the ground, which is a rarity in physics classrooms, but we're going to assume so for the sake of our math today. So, as we've just spent quite a bit of time talking about, pressure is force divided by area. So if we need to figure out how much force we have first. So the force that's going to be pushing down from our chair onto the ground is going to be the force of gravity. So if we're going to calculate that force, that's just going to be mass times the acceleration of gravity. We have both the mass of the student and the mass of the chair. So I'm going to say that that's 65 plus 5 kilograms times the acceleration of gravity, which is 10 meters per second squared. Or we're approximating it as such in this class. Or actually, let's do 9.81. I bet we can handle that. 9.81 meters per second squared. And so whenever we multiply those together, we end up getting 686.7 newtons. So that's our force. Then we have, this is our area of each chair leg, and we have 4 of them. So if we want to calculate our pressure, we do our force divided by our area. Our force is just 686.7 newtons. Our area is just our 4 chair legs that each that each have an area of 2.5 times 10 to the negative 4th meters squared. So if I just multiply this number by 4, which gives me 10 times 10 to the negative 4, and then I divide 686.7 newtons by that number, we end up getting 686,700 pascals, or 686,700 newtons per meter squared. Now I could also just divide this by a factor of 10 to the third to convert to kilopascals, divide by 1,000, which would give me 686.7 kPa. And that's all there is to it. Pressure is a force spread out over an area. So to calculate it, we just take our force and divide it by our area. So both force and area are concepts that you guys have spent a lot of time this year practicing with, so hopefully that's not too scary. But if there's anything we didn't cover or anything that's still confusing to you, please feel free to leave a comment and let us know, and we will do the best job we can to answer that question for you. But all said, thank you so much for sticking with me through all of this. Y'all are troopers, and happy physicsing.